Okay, I'm going to have a go through the energy transfer test and explain my reasoning for every answer I put. State what is meant by the conservation of energy. Well, sort of the main principle of conservation of energy is that the total energy in a system does not change, okay? Or the way that most people would go through it was energy cannot be created nor destroyed. Okay, which is what most people went for when they had a go at doing it. Okay, part B. Calculate the percentage efficiency of a motor which produces 12 joules of kinetic energy for every 36 joules of electrical energy supplied. So the formula for efficiency is our useful divided by the total supplied, the energy in, times 100%. So we put in there, our useful one is kinetic energy because it's a motor. So 12 joules of useful over 36 joules supplied. So 36 joules times 100% equals, what, 12 is a third of that. So that's a third times 100, 33%. Obviously your calculator can help you do that. Okay, state the energy transferred involved in the device and situations below. There's 4 marks, there's 1 mark per each one. So thereafter, just at least one transfer. Now transfer needs an sort of input and an output. So battery connected, well, battery has chemical energy, or energy in its chemical energy store, and that's transferred to electrostatic. Okay, and then we got a ball falling through a vacuum. Well, the ball had GPE, and just before it hits the ground, it's been transferred into kinetic energy. A nuclear power station, well, the nuclear fuel has an excess of nuclear energy, and that gets transferred as a power station into electrostatic. Obviously, there's lots of transfers between here and here. Because it's 1 mark each, it's just after the main transfer. But we could accept, I suppose, nuclear to thermal would also be a transfer that's involved. A wind-up radio playing music. Well, if it's playing music, it's already been wound. So it's not using the kinetic energy. Kinetic energy is not being transferred at this point because that's already done. When it's playing that wind-up radio, it's using elastic potential energy. That's the sort of stored energy that's inside anything that's wound up. So if you think about a wind-up watch, not like one of these, but a wind-up watch has springs inside and bent bits of metal, and as you wind it, you're storing that energy in a compressed spring or a stretched spring, depending on the side of the watch. So here, your elastic potential energy is getting transferred it's been transferred as via sound radiation, but it's been eventually transferred into thermal. We'd have to allow that. We'd also accept sound. If you're going to put thermal, I think you really would have to put the transfer that's happening here. So it's via sound radiation. Okay, would be down there as the transfer. Okay, but they will allow that one there. Draw a Sankey diagram for an electric light bulb that is 10% efficient. Okay, so we start off with a certain amount of energy, and some of that's going to be transferred usefully. For a light bulb, it says 10% efficient, so useful is 10%, so I'll make that quite small. And the useful energy in this case would be light energy. And then coming over here, our waste energy would be, well, I always do that when I draw them, that with no place for my arrow. We got it down there. This would be our waste energy, and this would be heat. And our total is over here, and that is electrostatic. Okay, so we've got electrostatic energy there, heat energy there, or internal energy or thermal energy, and light energy there. Okay, important bit, making sure that that is considerably smaller than that, and that I've labelled my energies with all the ones so we know what they are going to be. If we had grid here, we would have to measure these. If there's no grid, then I have to just show that I understand that the proportions should be sort of 10 to 90 in that sort of to I. Okay, question. Describe how heat is passed on by conduction. Okay, well, in a solid you have atoms which vibrate more when heat is applied. The vibrations are passed on to neighboring atoms, okay, through the bonds and so on. You could also talk about in metals, which are very good at doing heat by conduction because they've got free electrons. So in metals, free electrons gain kinetic energy and transfer the energy to metal ions via collisions. Okay, so let's start on this bit. Explain how the sun causes wind. Okay, well, the sun causes wind. Well, the first thing you have to do for wind, we've got this movement from hot air to cold. We also know that hot air rises. So essentially, the sun is going to be heating the ground. The ground is going to be absorbing the heat. Air is unlikely to heat much just from the sun. So it's more the ground is heating the air. So the sun heats the ground, and that could be any surface. You could be talking about sea or ocean or whatever. The sun heats the ground, which heats the air above the ground. Okay, so now we got some hot air. This hot air is less dense, so it rises. So now we've got this hot air rising off the ground. Okay, now the way convection current then works is cold air is then going to come in to replace it. Cooler air will move in to replace it. And as many of you mentioned, that's a convection current. That's a convection current. And this cooler air moving in is the wind, which is wind. There's that one moving there to replace. Explain how a boil blanket helps keep a person warm after they finish running a marathon. Well, after they finish running a marathon, there's an awful lot of respiration occurring, and there's an awful lot of sort of excess heat being emitted by our body. We're doing all kinds of things. Our blood vessels are dilated, all sorts of things. But the main point, as far as the physics is concerned, is you are warmer than the environment, okay, on the outside of that. So you are an emitter of heat. So what we need to do is make sure that emitted heat doesn't go into the environment, that the emitted heat comes back to you. Now, foil blankets is very good at reflecting heat. So foil is a good reflector of heat radiation. If we're talking about reflection, we are talking about radiation here. We're not talking about sort of hot air being reflected or some form of conduction through atoms. Radiation is the thing that reflects light, forms of light, in this case infrared light. Okay, so good reflective heat radiation. Okay, what this means is, so the heat is not emitted into the environment. It can be reabsorbed by the runner. Okay, you don't need all of that for the mark. It's really about saying good reflector and knowing that you're talking about radiation as the key point. Explain the purpose of trapped air pockets of air contained in warm clothing. Now, you're all quite right. It's acting as insulation, but the point is you've got to explain how it insulates. And the reason air insulates is because air is a poor conductor of heat. That's great. So we've explained why it's not conducting the heat away from our body. But there's other ways that air is really good at transferring heat through convection. So how does it stop doing that? Well, the point is they're trapped here. As the air is trapped, it is unable to move and transfer heat by convection. Okay, so we've explained the two ways that it helps us there. It's not going to conduct the heat away because it's a poor conductor, and because it's trapped, it's unable to move and therefore form convection currents. So it's not going to do that either. Describe an experiment to investigate how surface temperature affects the rate of emission of heat radiation. So the key bit here is surface temperature. That's our independent variable. That's the thing we can change. And then we're going to investigate the dependent variable, which is the rate of emission of heat radiation. So as something emits heat, it's going to cool down. So the key thing here is have at different temperatures, see how quickly it cools down. So the first thing I need to do is have different temperatures. Well, the easiest way to have different temperatures is just to literally wait for things to cool down. So if I put, many of you mentioned the Leslie cube, and as part, the Leslie cube starts off quite well because we've got a container that we put boiling water in, and it is indeed going to cool down. The problem is it doesn't say here, investigate how different surfaces. And a Leslie cube has different surfaces. So we're not really controlling another thing that could affect it. So a Leslie cube itself would not be an appropriate thing to start with. But let's go with partly what you said. Let's go with a metal box. So we could have a container. A container is filled with boiling water. Now I want to do it by radiation, which means one of the main things I could lose heat by is by convection. So I'm going to put a lid on with a lid to prevent evaporation and convection. Okay, now I'm going to put a thermometer in. Thermometer can be... Now, in terms of emission, we could put the thermometer on near it, but we could also just put it inside it because it's going to be losing heat from it in the water. Okay, now we can start stopwatch and record temperature, let's say every minute. Okay, now as it cools, it's going to be cooling because it's emitting radiation. So to see if this is the case, we could plot a graph of temperature against time. Now, if we did that, there's our temperature, there's our time. We're expecting a high temperature here, and as it cools, it will cool quickly, we think, at the beginning, so it will drop quickly, and over time, it will do that. Our gradient is getting less. And if our gradient is getting less, it means it's losing less heat as it gets cooler, or it's the rate of losing heat is getting less. So the gradient of the graph, the gradient will show if the rate is changing. Describe the relationship you'd expect to observe in the experiment above. Well, I'd expect to see this relationship here. The cooler the surface, the slower the rate of heat radiation emission. Okay, always use the words that are in the question. A box was dragged 5 meters across the floor. It took a force of 15 newtons. Calculate how much the work was done. Well, work equals force times distance. I've been given a force and I've been given a distance. So I just put the force in, 15 newtons times 5 meters. It's two significant figures, so make sure my answer's to that, and it's 75 joules. How much energy was transferred? Well, energy transferred is the definition of work, so that must also be 75 joules. Define power. Power means the rate of energy transfer. Okay, so the rate of energy transfer. Rate just means per second, so you could also have written energy transfer per second. Would be another way to answer that, but you have to state the seconds or use the word rate. It took 10 seconds for the drag the box across the floor. Calculate the power. So from one of the formulas I need to know, power equals work divided by time taken. So power equals, my work was 75 joules, my time taken was 10 seconds, so that equals 7.5, and my unit is the watt. A pupil holds a 0.05 kilogram pen, so that's my mass is 0.050 kilograms, 5 meters off the ground, and we're talking about gravitational potential energy here, so we're talking about the height. The height equals 5.0 meters. Calculate how much more gravitational energy the pen has than when it's on the ground. Well, G on Earth is 10 newtons per kilogram. So GPE equals mgh. M is 0.050 kilograms. G is 10 newtons per kilogram. And height is 5 meters. So if I do that, I've got 0.5, 2.5 joules. Okay. That was quite well answered by some of you. A pupil then drops the pen. State how much kinetic energy it has just before it's ground. Well, it had 2.5 joules at the top, and that was in the form of GPE, and it wasn't moving. And at the bottom, it has no GPE, so GPE equals 0 joules, and it's been transferred into kinetic energy, which must mean the kinetic energy has all the energy, because energy can't be created nor destroyed. So that means it must also have 2.5 joules. The same as I put on this one here. Calculate the pen's speed just before it hits the ground. Well, it says speed, and I've just worked out the kinetic energy. My kinetic energy formula is a half mv squared. So if I want to find the speed, I'm going to have to rearrange this. So I need to get rid of a half by timesing by 2. So 2 times kinetic energy equals mv squared. I need to get rid of the m by dividing. 2 kinetic energy divided by m equals v squared. I've got to get rid of the square, so that means I've got the root of the 2 times kinetic energy divided by m equals v squared there. Okay, let's substitute. My kinetic energy was 2.5. 2 times 2.5 is 5, divided by my mass, which was over here, 0.05 kilograms, and I need to root it equals v. Well, 5 divided by that is 100, so I've got root 100 equals v, so v equals 10 meters per second. Okay, that's the end of the test. I hope that helps.